Okay, so it's a pleasure to introduce to you Professor Woonam Lim from Yonsei University, and he's going to talk to us about Nekrasov's gauge origami via DT4 theory. Please go ahead.
Thank you very much for the invitation and introduction. I'm very happy to speak here. So first of all, I'm a mathematician, so my talk could be much more math-oriented than other talks. So I will explain joint work with Noah Albesfeld and Martin Kohl, where we try to understand Nekrasov's gauge origami theory, or maybe very small part of it, using purely mathematical theory called the Donaldson-Thomas theory of Calabi-Yau fourfolds. This is a rough plan. So I will start with the very old story, the classical instantons on two-dimensional theory. And I will review what's the relevant moduli space and some of the main properties of these moduli spaces. And of course, in between 2D and 4D, there is a 3D theory, but I will directly go into 4D theory and only comment on 3D theory very briefly. So there is a 4D theory developed by Nekrasov, which he calls gauge origami theory, and this parameterizes what he calls spiked instantons. I will introduce the moduli space, and I will try to make some analogy between 2D theory and 4D theory. And one of the main content of this talk is that on the left-hand side, we have an origami partition function, which Nekrasov defines. And from mathematical point of view, this is something defined only locally at each fixed point. And it was not clear that this comes from a global theory. And DT4 theory provides a global point of view. And a priori, they could be different, but our main theorem says that they are equal. And I'll try to comment on what this really means. And one of the main applications that Nekrasov had in mind was, I think, non-perturbative Dyson-Schwinger equations, which I will also explain in the end. Okay, here is a classical instanton. They admit three genuinely different interpretations, I think. This was originally developed on the space-time R4, or most of the time we will identify this with C2. Originally, this was given as an anti-self dual SUR connections on the space-time. So that's the Yang-Mills theory origin. But by Attia, Drinfeld, Hitchin, Manin, they classified all the solutions by using quiver representations of the quiver, which I will denote by Q of 2D. And then slightly after, this was given a purely algebrogeometric meaning, given in terms of Rankar vector bundles on P2. For a technical reason, we call this a frame shift because we are only interested in C2 part, and on the boundary of the C2, we frame it by fixing an isomorphism. Okay, so that's the three different interpretations. So let's recall what was the Q of 2D. So this is a framed quiver, and on the central vertex, we place C to the N, and the framed vertex, we have C to the R. And this is what's called the ADHM equation that these linear maps should satisfy. We call this representation a stable if the central vertex is generated by the image of I and sufficient application of B1 and B2. And if two such representations are given, we call them equivalent if they are the same up to an automorphism of the central vertex. So that's the classical 2D ADHM quiver. And this representation theory of this Q of 2D gives rise to algebraic Hamiltonian action. This means that if you look at the middle space, this parameterizes the space of all possible linear maps, B1, B2, which is recorded by endomorphism of Cn, and map of I and J follows. And if you look at the middle space, this is clearly a self-dual space, so there is a symplectic form. And then we look at stable part of it. And then this ADHM equation gives rise to a moment map, and this GLN action was the equivalence relation that I just explained. When we have a Hamiltonian action, we often do the Hamiltonian reduction to get a symplectic quotient. And by doing so, we obtain a moduli space of representation of this ADHM quiver QD, Q of 2D. And this is again symplectic in an algebraic sense or holomorphic sense. And this is just a small fraction of example of Nakajima-Kibble varieties. The rank 1 case, this becomes even more familiar object. So rank 1 case can show by some effort that J is always 0 if you are given a stability and the ADHM equation. So now we can ignore the J, and then you can see that, so by small v, I mean the image of the I map. And then because B1 and B2 commutes, because there is no J, you can easily show that this is isomorphic to Hilbert scheme of n points on the affine plane A2. And this admits a torus section, which was in the physics talk, it was called as a flavor symmetry. And then the corresponding fixed loci are given by integer partition of the number of points, or correspondingly, there is a monomial ideal description in this way. Okay, so and this is, of course, one of the best way to understand the Hilbert scheme of points by torus section. Okay, what about the general moduli space? If you have a Rankar instanton moduli space, they also admit a bigger torus section, which now also has a framed torus C star to the R. And then fixed loci, very similarly, is characterized by R tuples of partitions whose size sum up to n. And this moduli space, because it's constructed by a Hamiltonian reduction, this is algebraic symplectic. In particular, its tangent bundle and cotangent bundle are isomorphic to each other. And to be fully equivariant, we need to put some torus character here. And T1 and T2 was, I think, was denoted by Q1 and Q2 in the physics talk. And given this data, we often consider partition function. And in physics literature, this was called as a partition function with an adjoint matter. For mathematician, this is just putting the Euler class insertion of the tangent bundle by a twist of the non-trivial character. Okay, and this is the partition function that we can assign for the collection of our moduli spaces. And again, this partition function can be studied by this torus action. To state the formula, we need some torus characters. In mathematics, this is seen as an element in the equivariant K theory, what's called equivariant K theory. And the n denotes the sum of our framed torus characters. And pi is 1 minus ti. And yeah, this is the main part which corresponds to the fixed points corresponding to this tuple of partitions. And then this is t of lambda using this. Okay, and this P12 is multiplication of P1 and P2. Okay, and given these characters, we can Artiable localization formula and our description of the fixed locus express the partition function with adjoint matter in this formal sum up to tuple of partitions. Okay, and lastly, we have an instanton shift correspondence. So on the left-hand side, we have a Kibble moduli of Kibble representation I just explained. And on the right-hand side, we have a purely algebrogeometric object, meaning moduli of framed shifts on P2. What does that mean? So we consider P2 as a compactification of C2. So its complement is the boundary, which is a line at infinity. And then this moduli space parameterize a tuple of E and phi. E is the Rankar framed torsion-free shifts. So this torsion-free shift is basically a vector bundle with some singularity at finite many points. And phi is a fixed isomorphism on the boundary points. Okay? If you restrict this bundle to the boundary D, then this should be trivialized by this phi. And then the C2, some topological number attached to this frame shift corresponds to the instanton number n. And then surprising fact is that these two moduli spaces, even though they look very different, they comes from very different origin, they are isomorphic to each other. And correspondence is, I think, highly non-trivial except for the rank 1 case. For example, how do we obtain E, the torsion-free vector bundle or torsion-free shift or vector bundle out of the ADHM solution is the following. So over P2, we can consider following standard vector bundles. And then we consider linear maps given by this solution of ADHM equation. And the fact that they satisfies the ADHM equation shows that this is actually a complex, meaning that if you compose this, then it becomes 0. And also stability condition shows that cohomology is only at the center. And that cohomology shift is exactly E. And you can show that such a cohomology shift is naturally framed. So there is also data phi that you can obtain. And this is a natural bijection, so it shows that this is an isomorphism of moduli spaces. All right, so that's the brief review of the classical story. And in the, let me get into the gauge origami theory. So in a series of papers, Nekrasov initiated the gauge origami theory, and there are already many papers and many follow-ups that we already heard in this workshop. And his proposal was to study instanton, so more general type of space-time, which he calls origami space-time. So this is, roughly speaking, a union of coordinate surfaces instead of a single C2 living inside C4. Okay, so if you are considering coordinate surfaces inside C4, there are 6 of them. So here is a cartoon picture for 3-dimensional reduction. So from now on, I will denote the coordinate lines by small characters A, B, and C, and coordinate surfaces by capital A, B, and C. Okay, and they intersect in this interesting way. So, okay, what's the concrete proposal? He come up with what's called a 4D ADHM cuber, which I will denote by Q of 4D. So now instead of having just B1 and B2, we have B1, B2, B3, and B4. And also the framing vertex, instead of having just one framed vertex, we will have 6 of them, basically corresponding to the 6 coordinate surfaces. And then he proposed a generalized ADHM equation, where the first one is somehow looks very familiar to the classical story, but then second and third, they look like a new feature of this 4D theory. Okay, and as before, we have a notion of a stability condition, meaning that the center vertex is generated by image of I and sufficient multiplication of BAs, and then they are considered equivalent if they are same up to automorphism of the center vertex Cn. And we can define a moduli space in this way by considering solution of all Bi, Ia, Ja satisfying the equation and stability up to the notion of equivalence. And this is really a generalization of a 2D ADHM theory, because if you consider the rank vector in this way, meaning that you consider rank 1, 2 equals to R and everything else 0, then this is just nothing more than the classical ADHM moduli space. So it's natural to ask, can we generalize much of the story developed for Q of 2D in the 4D setting? For example, total section and symplectic structure, partition function, and what about the correspondence between geometric objects? Before we get into the general story, let me start with an example. So here is a truly 4D example, because we have a rank vector which spans all 4 coordinates. And then, but we will consider the smallest instanton number, which is 1. Smallest non-trivial instanton number 1. And then if we have to parameterize the solution of all ADHM equations, there are some classical ones that appears. For example, if we cut this picture into half and only look at the left-hand side, then this looks just like the classical instanton quiver. And then such a solution is indeed a solution for this generalized theory. And the same happens for the right half side. So we have at least the first 2 types of solutions are naturally there, meaning the classical ones just put into the first 2 coordinates, or third and fourth coordinate surfaces. But there is a new one coming in. If you set all the BIs to be 0, and if you consider the ratio between these I maps, I12 and I34, that's invariant under conjugation of C1, because that scales both I and I12 and I34. So their ratio remains invariant under such an action. So that becomes another type of solution up to this C star action in the middle. So the moduli space in this simple case becomes like this. The classical solutions give a plane which corresponds to Hilbert scheme of 1 point on C12 and another copy of Hilbert scheme of 1 point on C34. But then they are connected by this new solution which record the ratio of these I maps. So that's how the moduli space look like in this simple case. Okay, now let's get it to the general story. So there is again a torus action. This is our standard. So here we consider our scaling of our B1, B2, B3, B4, but in a way that it preserves the Calabi-Yau form. So that's the only restriction. And then still there are some framed torus action, which is now indexed by capital A corresponding to which surface we look at, and which stack of surface is indexed by this alpha. And this acts on the moduli space in a natural way as before. And then again, we have a correspondence between the fixed points under this action and the tuple of lambdas. The only difference is that we should consider these tuple of partitions as if they are sticking to which surface they come from. So that's the only difference. For example, this lambda 2, 3, they should be thought of as sticking to this coordinate, generally by second and third coordinates, and so on for the others. Okay. So the fixed locus description is very similar. It's just we need to think of them together with the surface. All right, what about the symplectic structure? The moduli space, as we have seen in the example just before, it's a singular, so it cannot be symplectic in the usual sense. But nevertheless, as the title suggests, there is some symplectic structure that we can put on this moduli space, and that is called a negative two-shifty symplectic structure. And just like the usual symplectic structure defines the isomorphism between tangent bundle and cotangent bundle, there is the negative two-shifty symplectic structure implies isomorphism between what's called tangent complex instead of tangent bundle and cotangent complex instead of cotangent bundle. And then there is a shift, which is the matching with this shift. But to say this, we need to choose what's called the derived enhancement of this moduli space that I just described. And this is some hidden structure behind the moduli space. And one of the most natural source of the derived enhancement that you can look for is to recall how the moduli space was defined. And the moduli space was defined by looking at some collection of linear maps, BA, IA, JA. And then they were required to satisfy equation. And in algebraic geometry, we can put that into this cartoon picture where this is a set of variables. This is a space of all the variables where B, I, and J lives. And then we consider zero set of this equation. And ADHM equations, they define the section of this vector bundle E, and its zero locus is the moduli space. And when your space is constructed by an explicit zero locus inside something, this gives what's called a derived enhancement on this moduli space if you take what's called a derived zero locus. And if you take a derived zero locus, your tangent complex for this derived zero locus is of this shape. But then this shape is not what we want because it clearly doesn't satisfy what I talked about, this -2 shifty symmetry. If this cotangent complex is given by dualizing this tangent complex, so they look like this, but then this -2 shifted to here. But you cannot say that these are isomorphic in each degree. So this is clearly not symmetric in this sense. So we need some additional information about our ambient space U and this vector bundle E and the section S. And that additional data we need is the following. So we need that this vector bundle that's cutting out the moduli space admits a quadratic form, which is additional data. And then we need that this section to be isotropic in the sense that if you apply this to this quadratic form, then it's 0. And whenever this is the case, there is a construction by Hyunjung Park called, who is here. It's called the symplectic zero locus construction. And once you do that, instead of a derived zero locus, this endows your moduli space with a new derived enhancement, which is -2 shifted symplectic in the sense of PTVV. And in particular, its tangent complex, if you take a symplectic zero locus, looks like this, which is obviously symmetric. So here, T is dual to the cotangent, and what's in the middle is self-dual by this additional data of a quadratic form. Okay, and the fact that this becomes even a complex is precisely because of this isotropic condition. All right, so this construction of the quadratic form actually comes from a certain splitting of the bundle where lambda is an isotropic subbundle. Okay, and the complement is a dual of this isotropic subbundle. And then there is a 3D version of the story. So 3D version is the same, but the additional structure that you have in the 3D case is that the bundle that's cutting out is actually cotangent bundle of the ambient variety U. And then the section S is given by the differential of some function. And when your moduli space is given by that, that's called the global critical locus. And this was the content of Repchap, Soilberman, Yang, and Zhao. Yeah.
How does this work in the specific example? Also, Q. So that was a concrete example of the moduli,
yes,
which was singular.
Yes.
And is it possible to explain somewhat concretely what this small Q does?
What this small Q is?
Yes, in that specific example, or is it somewhat more abstract, or let's say?
Actually, sometimes it's easier to describe the general case than the special case, but actually this is that case. So if you record the equations, the equation this is being 0 inside certain vector space. So if you take a commutator and plus ij, this lives inside the endomorphism of a C1, Cn. And then we have not just one of such an equation, but in total of 6 of them. And then, so now we have a 6 copy of endomorphism space. That's the part of our vector bundle E that's cutting out the moduli space. And that has a polarity form Q, because now if you have a coordinate A, then there is a complement coordinate, because we are living in C4 and we are looking at 2-dimensional subspace. And then we are taking a trace form between this complement and endomorphism.
Oh, I see. So that's the decomposition lambda and lambda star.
That's lambda and lambda.
Oh, I see.
Yeah.
Thank you.
Yeah, and of course we also need to take care of these, and they also are treated in a similar. Actually, this is taken. This is self-dual in that sense. These are also self-dual in the sense. This is dual to this, and that's how we put the quadratic form.
So you can do that construction for any rank vector?
This is for any rank vector. So this is, even though in the picture I put a single frame vortex, but there are 6 of them as in previous talks.
I mean, there is this quadratic form is there for any rank vector.
Yeah, this is general. Okay, and now we come to the partition function, and as I explained, this E admits an extra data of Q, and in fact that Q comes from a splitting of this isotropic part and the complement, and the section is isotropic, but if S were factored through lambda, this is obviously isotropic by the definition of isotropic subbundle, but it's actually mixed. So it's quite complicated as a local picture. But there is a theory to define innovative invariance of such a local picture, or actually even global picture, to define invariance in this local model. and that's called the autonomous virtual class. And this O is Jungsuk, who is here. And this is some notion of a virtual class living inside a homology, or if you're an algebraic geometer, this lives inside a child group of your moduli space. And this is this has an expected dimension, which is a virtual dimension. And the difference is that usually if you cut out your space by some equation out of an ambient space, the expected dimension is the dimension of the ambient space minus the rank of, minus the number of equations. But because of this isotropicity, the expected dimension is actually half of what we actually have. And one should think of this as a localized version of the following construction. So if you have some cycle here, the virtual class here, we can push forward there, but push forward class is much easier to understand. And the push forward class is basically what's called the square root Euler class of this quadratic bundle kept with the fundamental class of the ambient space. Okay, what does that mean? So if you look at the usual Euler class of E, then its Euler class is multiplicative. So it's multiple of Euler class of lambda times Euler class of lambda dual. But the dual has up to a sign. This is same as the Euler class of the original bundle. So basically up to a sign, Euler class of E has a square root, which is just Euler class of lambda. And then in that sense, this Euler class of lambda is a square root of Euler class of E. And this is basically what the autonomous virtual class look like. I forgot O here. So here O means the choice of an orientation data. And this orientation data is some choice of an isomorphism of this shape. And if you choose an orientation data that's coming out of lambda, then this choice of a square root is exactly Euler class of lambda. Because we are choosing some square root, there is always an ambiguity of a sign. But if you choose it from lambda, then this becomes Euler class of lambda. Okay, now using this autonomous virtual class, we can define the origami partition function in this way. So we just integrate one against the autonomous class and take a generating series, except that we normalize by the what comes as a result of n equals 0 part of this. This is just to make this power series to start with 1 instead of CR. We just normalize by this explicit constant. And then there is just like the Atiyah-Bott localization formula for smooth manifolds, there is a version of a localization formula by O. and Thomas for -2 shifted symplectic case. And this also express your partition function in terms of the fixed locus of the moduli space under the total section. And then if you look at what's written here, this is sort of a half of the virtual tangent space, because if you recall, this was how the virtual tangent space looked like for the moduli space. If you cut this into half, then the part that you have is a t, and the half of the middle guy, which is a lambda. Okay, so that's a kind of half of the Euler class already. So you have that, but then there is a difficult ambiguity of the sign, and that's kind of usually the main difficulty to study this DT4 invariance in mathematics side. But somehow, to us, very surprisingly, Nekrasov defined a different half coming from physics, I guess physics intuition. I heard that this is related to the JK localization formula. And then he defined a different half instead of what I just wrote, t minus lambda. He defined this v lambda to me out of nowhere as a mathematician. And then he write down this explicit formula. And then what this v lambda does miraculously is that this cancels out exactly the autonomous localization signs, which are very difficult to analyze in general. But in this case, if you use v lambda instead of t minus lambda, which is more geometric, then it removes all the signs. So basically what happens is autonomous sign is given by the parity of the following explicit vector space involving t and lambda. And then we show that dimension of this this cocorner of T fixed part of the cocorner is same as the following much simpler linear map. And this linear map, of course, depends on this which fixed point that we are looking at, corresponding to the tuple of partitions. And then such a dimension was computed by Kuhl and Venemo in their solution to Magnificent Four conjecture by Nekrasov and Nekrasov-Piazzolunga. And then that formula is given in terms of the partition combinatorics. It was related to the size of the partition and some hook lengths at the 0,0 up to 2. And then this difference, this non-trivial sign of the Automas localization formula was exactly the difference between Euler class of this, which comes as an Automas localization, and this was Nekrasov definition. So that cancels out all the sign. So if you use this, we have no simple formula. Okay, and okay, let me come back to the partition function. So
So fundamental class depends on the orientation.
depends on the orientation.
But somehow, after going through the partition function, dependence goes away, or like
So dependency is all remembered in this difficult sign.
yeah. So there is a sign. I see.
Yeah.
But I see. I see. So it depends on the sign, but it's just a clever change of variable to kind of disappear. Is that what is the state?
So the story is that actually, at least I couldn't. Nekrasov wrote this page origami paper around 2016, I think, and then for him there was no such a thing, because this, I think this purely mathematical theory has been developed much a little after. So he just used this as a from mathematics perspective, this was a definition.
Okay,
but
just
probably he had a physics
I see. But I just trying to keep track of what happened to the orientation data in this step. So in the previous slide there was orientation data, right? So plus minus sign.
Yeah. We choose some orientation here.
Right. And then where did it disappear in the next step? Then how?
This is because we changed it to V lambda instead of, so here we have a T minus lambda.
Yes.
And because T minus lambda and V lambda, they are not the same, but their Euler class differ by a sign.
I see. And then I see. So that's why the orientation data comes in.
Yeah.
They kind of cancel out. I see.
Yeah, they cancel out, and once you transfer to here, then we have no more sign.
I see.
Yeah. And then just like the moduli space of the 2D instanton was recovered by this specialization, so is the partition function. So if you consider gauge origami partition function on the left-hand side for this special rank, this is precisely the partition function with Ezra in order. And so this is a 2D special case, but we also compute some genuinely 4D case, which was the example that we considered with n equals 1. But for general n, we proved that there is a splitting formula, meaning that partition function for this rank splits into these rank 1 partition functions of classical instantons. And these rank 1 cases, they admit explicit formula there. So this partition function is equals to this. But let me explain why this splitting formula is a little bit interesting and surprising. Because as we have seen in this n equals 1 example, the moduli space doesn't split. What does that mean? We have a classical solutions corresponding somehow the right-hand side, but there is a non-trivial interaction between these two classical solutions given by P1 component. But the magic is that this P1 component doesn't contribute to virtual invariant or Automas invariant. And the proof is in roughly 3 steps. First, we observed that J vanishing also in this case. And I think this could be probably the last. So I already say that R equals to R12 equals to 1 in the classical instanton. If the rank is 1, J is 0. There is a similar vanishing in this rank, but I think this, except for this rank, there will be no other rank that this vanishing will happen. But in this case, we do. And using this, we can construct a equivariant proper map to the symmetric nth power. So if you look at this example, that would be just contracting this P1 to a point, because somehow they correspond to the same point inside C4. And then using this proper map, we can analyze the dependency of the partition function on the framing parameters, A12 and A34, and they are all independent of this. So we can take an explicit limit, which is easy to compute, and that limit evidently is splitting. So this is how we prove this partition function. And lastly, let me comment on the potentially geometric interpretation of these spiked instantons by some geometry of Calabi-Yau fourfold. Because we are using some Donaldson-Thomas theory of Calabi-Yau fourfolds, it's natural to expect such a formalism. And the natural place to start is C4 and its compactification, just as in the previous 2D case. And here we will choose a compactification done by 4 times of P1, and the D will be the complement divisor. The reason why we choose this explicit choice of a compactification is to guarantee this property, which is somehow useful in later point. So this is a cartoon picture for 3D reduction. So here, previously we had only parts connected to 0, 0, 0, but now we have added an infinity points, and then there are this D is the boundary divisor that we have. And if you compactify your original C2, then that will be called as a SA. And then SA meets the boundary at the broken line LA. Okay, so that's the geometry that we have in mind. And then we define the moduli of 2-dimensional frame shifts inside X. Just as before, it parameterizes a tuple of 2-dimensional shift together with how it behaves at the boundary as an isomorphism with this fixed shift. And then Chern character is defined in terms of n, the instanton number. And then the theorem that we prove is that this moduli space is actually a quasi-projective scheme. This requires actually the most significant effort for us. And then we also show that this admits a negative 2-shifted symplectic enhancement, just like in the Quiver moduli, 4D ADHM moduli space. And it admits the same torus action, and the torus fixed points are exactly in one-to-one correspondence with the Quiver side and with the matching virtual tangent character. And this was already a very strong evidence that there is a clear connection, there is some mysterious connection between these moduli of frame shifts and the ADHM moduli space, and we conjecture that they are actually globally the same, not just at the torus fixed points. Okay. And finally, I will finish by recalling some application of the origami theory, which is Dyson-Schwinger equation. So even though origami theory was a 4D theory, actually what Nekrasov had in mind was to apply this theory to the classical instantons. And that was let's recall the partition function of the 2D theory with the tangent bundle insertion. And this, let me remind you that this partition function satisfies some basic properties, namely homogeneity of for the these equivariant parameters, and there is a symmetricity on this S1 and S2, and you can also mix up AIs. There is also invariance under changing M to this, and this comes from the symplecticity of the moduli space of instantons. And then if you take a M equals 0 specialization, that basically removes this twist, and then just integrate the Euler class of the tangent bundle, but that corresponds to the number of fixed points. So this admits a very simple formula. So all of these are basic properties of this moduli of this partition function, but it's really hard to get the closed formula of this. And I think, we don't know what would be the correct way to study to this partition function, except for the rank 1 case. anyway, he introduced this origami theory to study Dyson-Schwinger equation that can be useful to study these partition functions. So how does it, so let me explain that application. So first of all, on the geometric side, Nekrasov proves the following. So I've already told you that this moduli space, if you use the full total section, that's just a bunch of isolated points, so clearly compact. But even if you look at some a little bit smaller subtorus, the codimension one, by imposing this equation on certain framing parameters, this is still has a compact fixed locus. And then to state the main result, let me define the following change of variable on the framing vectors. And then combining Nekrasov's compactness theorem and our main result that origami partition function can be given a global definition using Otoma's formula shows that for every, if you look at this partition function multiplied where this normalization factor is multiplied back, and then if you take a coefficient, negative coefficients by these parameters, they are all 0. And this is coming exactly from this compactness of the codimension 1 subtorus. And this equation turns out to be very interesting constraints on the partition function. So here is a very explicit example on the rank 1 case. So let's denote the rank 1 partition function by simply G of Q S1, S2, M. And the reason why I omitted A1 is because it's independent of the framing parameter in the rank 1 case. And then if you apply the Dyson-Schwinger equation in the previous slide, for the rank vector like this, together with this coefficient of x to the minus 2, this gives this functional equation on this partition function. And then using this functional equation, together with the basic properties of the partition function for general R that I mentioned, this uniquely characterized the rank 1 partition function. And that was, as we all know, this is just given by the number of partitions and then to some power. And this power is what essentially what this characterizes. Okay, and yeah, the rank 1 case was determined in this way. You can ask how much does Dyson-Schwinger equations constrain the higher rank partition function, which are much more mysterious. What I heard from Rak-Kyeong was that yeah, this doesn't really constrain enough to determine the partition function, but still I think there are some room to explore in this direction. So thank you very much for the listening.
Thank you for the very interesting talk. Any questions in the audience? Yeah.
Then my question is maybe more for Nekrasov for the thesis, but so when I'm thinking in terms of branes, so some D0 and D4 branes, well, the 4 branes are on CP planes. So I thought for general rank vector, it breaks also perspective and computer preserve by the deeper.
Yeah, sorry, I cannot do that.
I think either gave it such a discussion with this paper in this paper. So maybe remember the big view. Give this speech view. Let's use this representation. Yeah. Yeah. Yeah.
On the sixth set of the D4 grid, you actually need 4 for the other 2. Such that. So
that explains why you can always do stuff. That's
Yes, sir. A question from a non-mathematician. So your theorem with the quadratic form.
Yeah.
Does that mean that this this modular space has a symmetric obstruction theory?
No, it's something different. So that'll be for the 3D version that I just very briefly mentioned. So you can think of that as a Calabi-Yau. So symmetric obstruction theory is something usually happens for moduli of shapes on Calabi-Yau 3 or But if it's a modularized space of shapes on Calabi-Yau cores, then what I said here is what always happens for the modularized space locally. So on some open subset, your modularized space is always of this shape. Yeah.
Any other questions? Now let's try Woonam Lim again.